My immense pleasure to welcome Professor Prajakta. So she's a professor of computer science at Chennai Math Institute. So she did her undergrad in computer science from Government College of Engineering in Aurangabad and her MTech from IIT Bombay. She completed her PhD at the Institute of Mathematical Sciences at Chennai under the guidance of Professor Meena Mahajan. She works in the area of algorithms in general, and her interest is more in the area of matchings. She has lots of publications in top tier conferences and journals, and she's an amazing teacher too. I was very fortunate to attend a course on matchings and algorithms at while I was at CMI. I really enjoyed doing the course under her. So I hope all of us would enjoy doing this course with her, and make the most of the opportunity that we are getting today. Thanks a lot, Prajakta ma'am, for doing the course here. So I won't take any more of your time, and over to you, ma'am. Thank you very much.
Thanks, Aditya. And thank you. I thank a lot to the organizers for calling me here and giving me the opportunity. So, hello.
Yes, we can hear
Yes, ma'am.
you.
Actually, I have logged in from two devices because I am unable to share screen from laptop.
Okay. So you may have to log off from the audio from the other device. Sign out of audio because there will be an echo otherwise.
I see.
Uh,
Okay, I will disconnect audio from the other device.
yes. One of the device. Yes. Now it should be good.
Okay. And now I can share screen. No, the other login is not allowed to share screen.
Yeah, now you can. Are you able to? Yes. Yeah.
Now I hope it is visible. Okay. So hello everyone. I will be talking about broadly in the, my topic is broadly in the area of algorithms. I think all of you are more or less familiar with programming. And when you write a program, it is just giving a set of instructions to the computer to perform a certain computational task. Now the task may be to sort a list of given numbers or to find a maximum of the given numbers. Or there can be more complicated things like you might be given a set of cities and distances between certain cities, and you may want to find a shortest route from one city to another. So I think you are familiar with some of these programming tasks. So for every program, to write a program, you need to break down the given computational task into smaller steps so that each step can be executed in a, I mean, each step is kind of obvious. So this underlying breaking of a big task into smaller steps is nothing but an algorithm. And the next thing is to actually code those tasks in a particular programming language. So I will be focusing on this first thing, that is converting a big computational task or breaking down a big computational task into smaller steps so that each step is sort of obvious. It is just one small step. And another thing about algorithm, or even when you write a program, how do you know that your program is working correctly? What we typically do when we write a program is we execute it on a few inputs. And when it works correctly, we feel that it is correct. But then more theoretically, you kind of need formal proofs to say that the program will run correctly on every input. So of course you cannot try out every input because there are infinite number of inputs. So we need some theoretical proofs. And that is also one thing which I will focus on. So I will talk about a particular problem. All of you will soon finish your schooling in another 2-3 years, and you will go for college admissions. So I will talk about this college admissions problem. So how does it happen? I mean, there are so many students, there are so many colleges. Even in one college, there are different branches. If you take engineering, there are several branches of engineering, and the students, of course, they have preferences on what they want and in which college. So there are students, and there are colleges and branches. So I will right now not focus on branches. Just to keep it simple, we will only talk about colleges. So this we will not focus on for the time being. So suppose we have students, let's say there are 5 students. We are taking a simple small model, and there are 2 colleges. So these are students and these are colleges. Now, as I said, students have preferences over colleges. You always fill up a form giving your preferences when you apply in a centralized admission process. So for example, student S1 may say that I prefer college C1 over C2. Student S2 might say that I also prefer C1 over C2. But student S3 might say the other way, that is S3 might prefer C2 over C1. So these are students' preferences. What this means is student S1 prefers C1 more than C2. So C1 is S1's first choice and C2 is S1's second choice. Okay. Similarly, we will have preferences for all students. S4 will also have some set of preferences, and so does S5. So these are called as preference list. And well, colleges are also not okay with getting any student. Colleges also want good students, so they also have certain criteria. For example, some college might arrange students based on their aggregate marks. Some college may care only about physics, chemistry, maths, or some place like CMI might care only about maths marks. So even for colleges, the preferences are not uniform. So it may so happen that college C1 prefers, okay, I will write it. I will write them here. So college C1, let's say, has this order on students. College C2 might have some other order. And there is a centralized authority who takes such preferences from students and colleges, and then students are allotted seats in colleges. And this is the problem that we will focus on. If one wants to do it, or one wants to write a computer program for this problem, how it should go. And in fact, first of all, what should be called as a good allocation of colleges to students. So let's say we do this allocation. So we assign students S1 and S2. Let's say we assign students S1, S2, S3 to college C1 and S5, S4 to college C2. Now we can see that college C2 likes S3 more than what the students that it gets. Right? So C2 likes S3 more, and even S3 likes C2 more than C1. Right? So S3 likes C2 more than C1, and C2 also likes S3 more than S5 and S4. So this kind of situation we call as instability. So C2, S3 we call as an unstable pair. Why do we call it unstable? Because C2 might say that I will not allot my seat to S5, S4, but I will allot it to S3. And S3 will also happily leave college C1 and join C2. So although central authority allots this kind of, central authority comes up with this kind of allocation, the college and student may not respect it. So they will not respect the allocation. Or we can say they will not follow the allocation. Right? So what we want is an allocation where such instability will not exist. So is it clear what we are looking for? If you have any questions at this point about what we want, please ask.
Hello, ma'am. So do we have a preset number of vacancies per college that college 2 can take only 2 or college 1 can take 3, or is that free?
This is a good question. Actually, yeah. So we will have fixed number of seats. So let's say here college C1 has 3 seats and college C2 has 2 seats.
Oh, all right, ma'am. Thank you.
Any other question? Okay, so let me write down our goal here. Goal is to output an allocation such that no student and college prefer each other over their allotted ones. So student doesn't prefer the college more than, it doesn't happen that both student and college prefer each other over what they are getting. So this we call, I will also introduce another term that is called as blocking pair. So a student SI and college CJ is a blocking pair if SI prefers CJ over his or her allotted college, and CJ prefers SI over its, I should say one of its allotted students. And our goal is to come up with a pairing which does not have any blocking pair. Output a pairing or allocation that has no blocking pair. Such a pairing is called a stable pairing or stable allocation.
Excuse me, ma'am, there's a question.
Yes.
Mokshit, you can ask your question.
It's not necessary that all conditions will have a stable pairing, right?
Okay, so that is, we have several questions now. So I will list down the questions that are there. So I will write, does a stable pairing always exist? Of course, how to come up with it if it exists is another thing. So let's look at this example at least. Is there a stable pairing here?
Yes, ma'am, there can be.
This one?
No, I don't think there is stable pairing.
Okay, so whoever thinks there is one, can you please tell me?
Yes, ma'am. I think there is one stable pairing.
Ma'am, there is one stable pairing.
Okay, please tell.
S1, S2, S5 in college 1 and S3 and S4 in college 2.
Okay, so S1, S2 and S5 in college 1, S3 and S4 in college 2.
But college 1 prefers S4 and S3 over S5.
Say it again.
No, ma'am. Like, but when we put S1, S2, and S5 in college 1 prefers S4 over S5.
College 1 prefers S4 over S5. But our notion of blocking pair says that both student has to prefer the college and college has to prefer the student.
There would be no stable pairing there.
No, so here, although college C1 prefers S4 over S5, S4 does not prefer C1 over C2. Right? So S4 C1, is it a blocking pair? It is not. I see lots of chat messages. Actually, S1, S4 in C1 and rest in C2. That is not, yeah, C2 has only 2 seats. Yes. So we need to allot 3 students to C1 and 2 students to C2 because those are the number of seats. Because if seats were not limited, we could have given every student the first choice. In fact, here it turns out that every student is still able to get the first choice. So let's go over the definition of stable pairing and blocking pair once again. So we call SI-CJ a blocking pair if SI prefers CJ over his or her allotted college and CJ also prefers SI over one of its allotted students. So if both these are true, then only that pair forms a blocking pair. Okay, so coming back to our example, because every student is getting the first choice here, there is no situation where a student would prefer some other college more than the allotted one. So if we look for a pair where a student prefers some other college more than what he or she gets, and the college also prefers the student, the first thing is not going to be true. Every student gets the first choice. So there is no question of any student preferring another college more than what he or she gets. So the question is this pairing stable?
Yes, this pairing is stable.
Say it again.
And that is because this pairing is stable because there is no blocking pair. Because because every student has their first choice.
Correct. So there is no situation where a student would prefer some other college, another college more than his own. So there is no blocking pair. So here there is no blocking pair because every student gets the first choice, first preference. So at least in this example, there is a stable pairing.
Yes, ma'am.
Shall we modify this example a little bit? So instead of, yeah, question?
Actually, I found one more stable pair.
Is there one more stable pairing?
Yes, S1, S2, S4 in college 1 and S3 and S5 in college 2.
Okay, let me see. I will mark it first. I will mark it with a different color. S1, S2 and
S4 in college 1.
okay. Oh, sorry. This one and S3 in C2 and S5 in C2. Yes. Let's check if this is a stable pairing. So here S1, S2 and S3 get their first choices. So they are not going to form any blocking pair because they don't prefer the other college more. Let's look at S4 and S5. So S4 prefers C2 more. But what is C2 getting? C2 is getting S3 and S5.
Yeah, S4 is C2's last choice, so there will be no pair containing S4.
Right. So because although S4 prefers C2, C2 does not prefer S4 over the students that it gets. So S4 and C2 don't form a blocking pair. What about S5?
For S5 also, it is the last choice of C1, so there will be no blocking pair containing S5.
Correct. Very nice. So, I'm happy that you are getting the concept of stability and yeah. So now we have seen that in this example, not only that there is one stable pairing, but in fact there are two. Right. So at least what we have observed is there can be multiple stable pairings. So let's write down this observation. So we have observed that there can be multiple stable pairings. Now another thing to observe is in the green pairing, every student was getting the first choice. So from students' perspective, the green pairing was better. Whereas from college's perspective, the red pairing is better. Do you see it?
Yes, ma'am.
So one pairing may be better for one set of entities and another pairing might be better for another set of entities. Okay, shall we move on?
Yes, ma'am.
instead of directly proving that a stable pairing always exists, what we will do is we will see how we will try to find out a stable pairing, and then we will say that our procedure always succeeds. So now our goal is to design an algorithm or a procedure to find a stable pairing. Now, when you design this procedure, there is always a possibility that the algorithm fails, and at the end outputs that there is no stable pairing. So we will now see that such a thing does not happen. So let me first tell you the procedure, but even before I tell this procedure, one more thing I want to do, that is, here we had students and colleges, and we also were concerned with the seats. Right? There were multiple seats in each colleges, and that is very natural. What we want to do is to take a simpler problem where there will be just one seat in each college. So instead of saying students and colleges, I mean, it is a bit unnatural to say that every college has one seat. So what we will do is we will call these, instead of students and colleges, we call them as men and women. So we have men on one side and women on the other side. So you can say that the men and women are to be paired, let's say for matchmaking or for mixed doubles in some games. So for whatever reason, we want to pair them up. Again, why we are taking this is because we don't want to deal with seats right now. We want to simplify the problem. So we want to take a situation where one entity from left can be mapped only to, or allotted only one entity to the right. So this will be a one-to-one pairing. So the new goal is pair men with women. So this is the standard terminology, and if you look at the stable matching literature, there are very nice, there is very nice reading material on this topic. So if you look at the literature, it is always stated in terms of men and women for the one-to-one setting. By one-to-one, I mean nobody can get multiple matches. Earlier, colleges could get multiple matches, but we don't want to go with that situation because having multiple seats makes it a little difficult. Our proofs and algorithm will be much simpler with this men and women setting.
Ma'am, just to clarify, if we have the previous instance, if we consider the previous problem with colleges and students, we can just, if the number of colleges is less than the number of students, then we can just copy every college. For example, college 1 had 3 seats, so we can make 3 copies of college 1, and then we can have that every college needs like one seat, has one seat, and then we can use this algorithm.
Exactly. Yes. So here colleges had multiple seats. We could have made as many copies of a college. So it would be like matching students with seats rather than colleges. But then it's a little bit problematic because a student will not have preferences between 2 seats in the same college. So that might be
right. Okay. But what if we randomly decide the preferences between 2 seats of one college? Will that work?
Actually, doing that randomly, we can just say that the first seat of any college is preferable to all students over the second seat of the same college, and so on.
Okay.
But as I said, it sounds a bit strange that one student is matched only to one college or one seat. So we will go with how things are written in the book, and instead of calling them students and colleges, we will call them men and women. So remember that the names are different, but everything else is the same. Again, there will be preference and there will be blocking pairs.
Okay, ma'am. Thank you.
In fact, here for the sake of simplicity, we will take equal number of men and women. And there will be also preferences as before.
Isn't the one-to-one pairing only possible if we have like an equal number of entities?
Yes.
Or else like some of them wouldn't have a pair.
Otherwise, some people will not get any pairing.
Yes.
So let's look at this example little more closely, and we will also execute our procedure on this example. So let me just write down the preferences now. Okay, so these are the preferences. Now again, let's try to first find out some stable pairings by inspection. Oops, sorry. What?
I think you'll have to go to the other note, which is college admission. Yeah.
Thanks. Okay, good. I think I by mistake clicked on new note and it became like that. Okay, good. So here, can we again observe some pairing which can possibly be stable?
I found two such pairings.
Okay. Yes.
M1W1, M2W2, M3W3, and same with
Okay.
then
Wait, I will match this also in women's side. Okay, one is the blue pairing. Next one.
I also have another one. M1 with W2, M2 with W3, and M3 with W.
Okay.
I also got one.
Okay, good.
M1 W3, M2 W1, M3 W2, then again the same thing.
I see. Okay, so good. We have three stable pairings here. I mean, we are claiming that it is stable, but we need to check that. And I'm glad that many of you have got lots of pairings. Okay, so clearly, if you look at the blue pairing, that is M1W1, M2W2, and M3W3, every man is getting his first choice. So if we again look at our definition of blocking pair, no man is going to prefer another woman over who he is paired with. So trivially, this pairing will not have any blocking pair because any man is not going to participate in a blocking pair by preferring another woman. Now same thing is true for green pairing from women's side. So if you look at the green one in the women's side, every woman gets her first choice in the green pairing. So every man gets first choice in blue pairing. So it is stable. Secondly, every woman gets first choice in the green pairing. Is it clear why I am saying that there is no blocking pair if one side completely gets the first choice?
Yes, ma'am.
Yes, ma'am.
If anything is not clear, please ask. Okay, so because every woman gets the first choice, there is no woman who will prefer another man over who she is paired with. Now, what about the red pairing? Nobody gets the first choice, so we have to be a little more careful, right? Right, so let's look at the red pairing. Let's see if M1 participates in a blocking pair. M1 gets W2. So M1 prefers only W1 more than that. So if M1 participates in a blocking pair, that could be only with W1. But for W1, M1 is less preferred than her red match, that is M3. So M1 W1 cannot be a blocking pair. Now if we look at M2, M2 gets W3 in the red pairing. So he can participate in a blocking pair only with W2. But then for W2, her red match M1 is more preferred than M2. So M2 W2 also does not form a blocking pair. And similarly, if we do for M3, M3 can only form a blocking pair with W3 because M3 prefers W3 over his red match W1. But then W3 doesn't prefer M3 more than her red match M2. So the red pairing, although nobody gets first choice, it is also stable. So let's also write down this observation that there can be a stable pairing when nobody gets the first choice. Is there an unstable pairing as well? Or are all pairings stable?
All of them are stable.
But apart from what we have written, the three pairings, is there a fourth one which is possibly unstable?
I think any pairing will be stable for this example.
Yes, any pairing can be stable.
Maybe M1 W1, M2 W3, and M3 W2.
M1 W1, I will mark this.
So along the diagonal in any of the 3x3 grids are drawn.
So this pairing, is the yellow color visible?
Yes.
So let's look at this yellow pairing. M1 W1, M2 W3, M3 W2, and similarly on this side M1 W1, M2 W3, and M3 W2. Let's see if this is stable or not. Can you check it quickly?
It's stable.
So M1 will not participate in a blocking pair. M2 can participate in a blocking pair with W2, but W2 is getting her first choice, so W2 is not going to form a blocking pair with M2. What about M3? M3 can be in a blocking pair with either W3 or W1.
Yes, every pair here will be a stable pairing. That is because at least one man gets his first choice and at least one woman gets their first choice. And they have to be distinct. So M1 and W1 can't both get their first choices. So MI gets their first choice and some other WJ gets their first choice. So the remaining pair can't switch or can't be a blocking pair. So at every instance will be a stable pairing.
So let me mark another pairing. So let's say I want to mark M1 W2 W1 and M3 W3.
Oh, sorry. 1 second.
What about this one?
This one is also stable, I think, because M3 it cannot switch and a W1 also cannot switch, and the third one is
Yes.
once.
It's
Yeah.
basically, so since we took in the previous example, the yellow one, we took the diagonal of the men's side, and here we are taking the diagonal from the women's side.
Right, right.
It's basically
Yeah.
symmetric.
Yes. Yeah, so we see that there are in fact lots of stable pairings. But of course, as we saw in the earlier example where there were students and courses, not every pairing need to be stable, because there we had spotted one unstable pairing as well. So now let's design a general procedure to come up with a possibly stable pairing. So this algorithm is called the Gale-Shapley algorithm. So this procedure goes like this. So this is like every man goes and approaches the first woman on his list, and the woman accepts or rejects depending on who all actually approach her. So let me write down a different example, because this example has like almost all pairings stable. So let me write down a different example here, and we will execute it on that.
Wait, ma'am, I think the example we took will have every pairing as a stable pairing.
Sorry?
In the example we took, every pairing will be a stable pairing.
So looks like
Ma'am, isn't M2W3 an instability in the blue matching? Because
W3 is it?
M2 prefers W3 or W1 and W3 prefers M2 or M3.
Correct, right. Thanks for pointing out. Okay, let's come back to this one. Yeah, so for the blue pairing, M2 prefers W3 and W3 prefers M2. Right? So in fact, for the blue pairing, M2 W3 is a blocking pair. It's very good.
Ma'am, also in the yellow pairing, M3 and W1 is a blocking pair.
Actually, yeah, that's what I'm also thinking. In the yellow one also there should be a similar thing. Maybe W1 participates in a blocking pair for the yellow pairing. Doesn't look like.
W1 M3.
Yes. W1 M3. This is a blocking pair with respect to the yellow pairing, because M3 and W1 both prefer each other over their yellow matches. And similarly, M2 W3 is blocking with respect to the blue pairing. Yes, good. So we had unnecessarily passed them as stable pairings, but they are not. So the yellow and blue ones are actually unstable. Any questions so far? Someone also asked, what if all men have same preferences, right? And all women also have same preferences? So would there still be stable pairings? I will answer this. In fact, we will take one such example and execute our procedure on that. So let's, just for the sake of it, try out. An example where everybody has the same preferences.
In that case, if we match M1, W1, M2, W2, M3, W3, I think that would be a stable pair.
Yes. So instead of now finding them by inspection, we will execute our procedure so that we will move on with the procedure, and we will also get on with the formal proof of correctness. Okay, so now here, as I said, the men one by one will approach uh, the women they prefer, and the women will accept or reject. So here first M1 will, any man can start. So let's say M1 starts, and naturally because W1 is the first choice, M1 will approach W1. Now so far W1 doesn't have any proposal anyway, so W1 will accept. So this is accept. Now that M1 and M1 is already paired, M2 will now go, and M2 will again approach the first woman, that is W1. So now W1 is already paired with M1, and now when M2 approaches, W1 checks between M1 and M2. So W1 checks her list. She prefers M1 more than M2. So she will reject M2. This leads to a rejection. Now M2 has to go ahead because M2 is not yet paired. So because M2 is rejected by W1, M2 will go ahead in his list and will approach W2. And W2 is not, nobody has yet approached W2, so W2 will accept M2. Now that M1 and M2 are paired, M3 will start. M3 will first approach W1, but W1 doesn't like M3 more than M1. So W1 will reject M3. Now M3 will go to the next woman on his list. So after W1, the next woman on M3's list is W2. So M3 will approach W2. Again, W2 will compare between her current match, that is M2, and the new proposal, that is M3. So between M2 and M3, W2 prefers M2. So then W2 will reject M3. Finally, M3 will approach W3 and W3 will accept. So this procedure where men approach women and women either accept or reject, this has given us a pairing. So this is the pairing. Can you check if this is stable?
Yeah.
So how a doubt?
Yes.
In a pairing, if like the first indice is already paired with someone else, then we don't consider that to be a preference, you know.
Say it again, sorry. Your voice is a bit low for me.
Like for example, we have paired W2 with M2, ma'am.
W2 with?
M2.
M2, yes.
W2 prefers M1 over M2, ma'am. So, but M1 is already paired with W1. So W2 M2 is not is a stable pair, ma'am.
Yes, M2 W2 is stable because although W2 prefers M1, M1 doesn't prefer W2 over his current match.
Yes.
Right. So M1 W2 is not a blocking pair because M1 doesn't prefer that more than his current match. So you can check that this pairing is actually stable, because no matter which pair you take, either the man doesn't prefer that woman over his current match, or the woman doesn't prefer the man over her current match. You can try it out for all pairs and see that there is no blocking pair. Okay, so at least in this case, this procedure has given us a stable pairing. Now here unnecessarily we said that M1 will approach first and M2 will go next and M3 will go after that. What if they don't go in this order but go in some other order?
So let's say first M2 goes.
Okay.
Then also this will be same, right?
Will it be the same?
Yes, because M2 will approach W1 first according to the list. So, but W1 prefers M1. So, W1 will go to M1, and M1 will accept W1's proposal.
Yes. So you can check that even if men propose in a different order, it will give still the same pairing. Okay, so this
Would that
sorry, yeah.
would that imply that there is only one stable pairing to this?
In this example, actually, yes.
Yeah, because in the algorithm, if a set has different like multiple stable pairings, then the algorithm would depend on where we start from. But since in this case there is only one stable pairing, it doesn't matter how we start. Will that be the case?
So let's see. Shall we try one more?
I think we can use the above example because it has two stable pairings.
It has actually three. Yeah.
Oh yeah, three stable pairings, and we can check with the algorithm on that. So
Okay, so what will our algorithm give on this earlier example?
M1 approaches W1, but W1 will not accept M1 because M1 is the last preference.
That is no, that is not correct.
Okay, it will accept it, but when M2 or M3 go propose, then W1's preference will shift to M2 or M3.
Right. So if a woman is right now free, is not approached by anyone, she accepts whatever proposal she receives.
And then when the next proposal comes, she shifts.
Yes, because even if the woman says, that is, even if W1 says that I don't like M1 much, I want M2 or M3, it is not clear whether they will ever approach her. So,
all right.
Okay. So, yeah, here, when M1 approaches W1, for the W1 will accept. Someone is...
Yeah, and then M2 will approach W2 and W2 will accept, and then M3 and W3 will also get paired. So the output of this should be M1, W1, M2, W2, and M3, W3.
Yes. So here it will be very straightforward. That is, if M1 approaches W1, for the time being W1 will accept. M2 will approach W2. W2 will also accept for now because she doesn't have any better proposal. And M3 approaches W3. Same thing. W3 will again accept because she also doesn't have a better proposal.
But if we run the same algorithm from the women's side, we would have W1 M2 pairing, W2 M3 pairing, and W3 M1 pairing.
Yes. So very good. So although men proposing in any order seems to give the same pairing, we will again prove it formally. But only what we observed is the pairing that we obtain by men proposing may be different from the pairing that is obtained by women proposing. Okay, there is a question in chat. Is there a way we can optimize this and not list all the pairs? This is probably for the checking of blocking pairs, right? So this observation at least I will write, that is, the men proposing pairing can be different from the women proposing one. There is again a question. So this algorithm states that until or unless we get any rejection, there are no chances of blocking pair. Yeah, even if there is a rejection, it is not clear that that is going to create a blocking pair, because the one who rejects it for better partner. Okay, now one by one we want to figure out the properties of this algorithm. See, what we have seen is on the two examples, this algorithm has given us a stable pairing. But that doesn't mean it will always give a stable pairing, that we need to prove. So first of all, will this algorithm pair all the men and women? Or will some people remain unpaired? So the question is, will all the men and women be paired by this procedure?
Since there are 3 men and 3 women, and like at the end there will be a woman and a man left, and they wouldn't have another choice but to get paired, I think they should be.
Yes, very correct.
Ma'am, I think yes, ma'am. All the men and women will eventually find a path.
Yes. So again, how we state this is, if there is an unmatched or unpaired man, then there is also an unpaired woman, because there are n men and n women for some n. So we have n men and n women. N can be anything. 10. I mean, here n is 3, but it can be any large number as well. If there is an unpaired man, then there is also an unpaired woman. But then why didn't that man approach that woman? That man must have approached that woman, and she would have accepted, because she doesn't have any other proposal either. If there is an unpaired man M, then there is also an unpaired woman, say W. But then M must have proposed W, and no woman rejects a proposal unless she has a better one. And W must have accepted, because in the end she is unpaired. Another thing to observe is, a man who is paired at some point, can he get unpaired later on?
Yes.
Yes.
That can happen, right? For example, if M2 proposes to W1 first, W1 will accept for the time being. But when M1 proposes, W1 will reject M2 and accept M1. So earlier M2 was paired with W1, but now M2 will again be unpaired.
And just like that, some man could be waiting for the woman right now, or something like that.
Sorry? Say it again.
No, ma'am, we were saying like if there is one unpaired man, there would be also an unpaired woman, so that man could approach that woman and give a proposal, right, ma'am?
The man must have proposed that woman at some point, right?
If it's like first M2 approached W1 and W1 has accepted it, but M1 doesn't, then M1 could have waited for, it's still waiting for W1 or some kind of sort, you could say.
See, what every man does is, every man looks at his list, approaches the first woman, if accepted, well and good. If that woman rejects that man at some point, he goes to the second woman on his list, and so on.
Okay.
So if a man M is unpaired and a woman W is also unpaired, W is also there on M's list. So at some point, M must have approached W.
Okay. Yes.
And can it so happen that a woman who is paired now can get unpaired later?
No.
M reject W now, so maybe a paired woman now can be an unpaired woman later.
Sorry, who rejects?
No, ma'am, can't M reject W, ma'am. If like women are proposing, then a paired woman right now could be an unpaired woman right now.
No, so we should look at one-side proposals. So right now when we are looking at men proposing, we should prove all the properties with the men proposing view.
Okay.
Symmetrically, women proposing will hold, but we will not mix up the two. So when men propose, men are not the ones who accept or reject. Women are the ones who accept or reject. So the question is, when men are proposing, can a woman get unpaired later on after getting paired?
No. So a woman, if she's paired now, she is paired with one of her preference, and she'll only change that pairing if a better proposal comes. But in no way can a man now change his pairing. So now a man cannot reject the woman and go to another like a W2 or W3. And the woman can only change if she has a better pairing, in which case she will still be paired. She'll not be unpaired.
Yes. So very good. I will also note this down first. So this is another observation that we have. A woman, once paired, never gets unpaired. And a man, once he is paired with a woman, he cannot on his own break that match and approach another woman. Unless he gets rejected by that woman, that man cannot move on in his list. So once a woman is paired, she might reject that man later on if she gets a better proposal. But she will never get unpaired. That is why when we said that if there is an unpaired man in the end, then there is an unpaired woman also in the end. This woman must not have received any proposal in the first place. But then what happened to M? M must have proposed W. And since W had no other proposal, W must have accepted. So this cannot happen. That nobody can remain unpaired in the end. And will this procedure ever terminate?
Yes.
Yes.
After
yes.
Okay, why do you say so?
Well, we can kind of we can make it a little. We can alter it a little bit to make it obvious determinants by making sure that if a man proposes to a woman once, he won't propose to her again, like when he's unmatched later. In this, because we can one observation is that in this algorithm, men only get sadder and women only get happier. So in that sense, once a woman rejects a man, that's only because she got happier. If she has a better preference, and she'll obviously reject him if he asks again in any point of the algorithm. So we can alter it to an equivalent algorithm by saying that a man can only propose to a woman once, and now it's obvious that it terminates because there are only a finite number of pairs you can form between n man and n woman.
So let me just, so I never wrote the algorithm formally, but it is clear that every man proposes to a woman at most once. There is no point in proposing second time because already the woman rejected him because she found a better match. So every man proposes a woman at most once. So there can be at most n square proposals. And I will also write this, that women get better and better throughout the execution of this algorithm, and men get worse and worse. Now, one important thing that we need to prove is that this algorithm will always give us a stable pairing. So this we need to prove. So do you first of all think that this algorithm will give a stable pairing, or do you think there might be instability?
The fact that women only increase in happiness and men only decrease in happiness proves.
Okay.
Ma'am, like we can write men as 0 and women as 1, a binary sequence.
Actually, I couldn't hear properly.
A woman only accepts the best match she gets, so it will always be a stable pair.
Yes. So we will prove it little more formally. We will say that suppose this pairing is not stable. Okay? So for the sake of contradiction, let the algorithm output an unstable pairing. Now suppose because the pairing is unstable, we are assuming like that there is a blocking pair, suppose MW. So suppose the algorithm doesn't output a stable pairing, so there must be a blocking pair. Let's say that blocking pair is MW. So here is M, here is W. This is a blocking pair. And suppose M gets paired with W1 and W gets paired with M1. This is the picture. So we carry out this whole algorithm. M gets paired with W1, W gets paired with M1, but both M and W like each other more than their current partners. So because M likes W more than W1, M's list looks like there is somewhere W and later on somewhere there is W1. Similarly, W's list looks like there is M and somewhere later there is M1. So then M must have approached W before approaching W1. And then W rejected M. Because otherwise, why would M go ahead and propose a worse woman in his list? So when M approached W, W must have rejected M. But then why is W paired with M1 now? If W rejects M, that would be only for a better partner. So it cannot happen that W later on accepts a worse proposal. So there cannot be a blocking pair like this, and the pairing is going to be stable. W must have rejected M. Then she cannot get a worse partner. Okay, so we have more or less said that this algorithm gives a stable pairing. So next tomorrow also we will talk more about this, and we will observe some more interesting properties. So we have already seen that there can be many stable matchings or stable pairings, and they have certain nice structural properties. So we will explore these properties slowly. We will also see some more interesting things about this algorithm. So this whole work on stable matching that Gale and Shapley initiated, and later Shapley and Roth and other people carried out. This work was given Economics Nobel Prize in 2012. This work is very deep. It has had a big impact on not only the area of algorithms but also economics and game theory. So there are several things to think about here. Since we don't have that much time, I won't now go into any formal proof, but I will let you think about a few things. So first of all, the way we wrote this procedure, that is men approach women and women keep getting better and better, and men keep getting worse and worse. And we also saw that men proposing algorithm gives one stable pairing and woman proposing one might give a different one. Because here we had this multiple pairings example. So this blue pairing was obtained by men proposing, and this one was obtained by women proposing. The green one.
Excuse me, ma'am, sorry to disturb you, but is it possible for you to move closer to your microphone? Your voice is a little distant.
Oh, is it? Okay. Is it better now?
Yes, yes, it's much better. Thank you.
Thanks. Okay. So between men proposing and women proposing, is it going to be the case that one way is better for one of them and another is better for another? Like, is men proposing better for men or women, or and similarly, what about women proposing? Is there any particular advantage that one party gains over another?
So it's clear from this example that the blue underline pairing is better for men since they get all their first preferences. So their proposing in essence gives them the better pairing. And like I think the green pair, yeah, the green pair is when women propose and they get their first preferences, so they are better off.
Yes. So although it looks like men keep getting worse when men propose, actually that gives the best pairing for men. That is a unique best pairing for all the men simultaneously. When it looks like they are competing with each other, but actually they get their best possible stable partner when they propose. So let me write down these properties. We will prove them tomorrow, but you can also think about why they might be true. So men proposing gives the best possible stable partner for each man. similarly women proposing. And I also want to say that men proposing gives the worst possible stable partner for each woman. So I will not prove this formally, but we will prove this in our tomorrow's session.
I think you wrote it opposite.
Sorry? No, this is what I mean. Incidentally, in our example with multiple stable matchings, we see that if men propose, every man gets the first choice in this example, and every woman gets the last choice. That is not a coincidence. Actually, when men propose, the women get their worst possible partners. So there can be multiple stable pairings.
Yes. Okay, let us say that I make the algorithm a bit different. Okay, so this is not a time, this is more like a time consuming algorithm, but I just want to ask what properties will it be. So let us say that after every iteration of proposal, giving proposals and getting proposals, the men band up and they tell each other what they did, and the women also tell each other what they received, and then they given the ad information, figure out the part that it is most likely to take, and figure out that whether accepting or destroying is best for each of the women and best for each of the men. So what if there's a more what if everybody is a perfect player instead of just thinking one step ahead, like right now?
Men propose and women accept or reject, but then they share the information with each other and make some plans, is it?
Yes. So now they have all the information all of the other women have, right? So then using that much information, they figure out or they check out which value should they accept or reject to find out to see if that is their best possible outcome. Okay, so they figure out what is their best possible method, given that the men are also doing this. Okay, and they know that both of them have the same information, so they figure out what. So both of the sides figure out what is the path that the other side will take, and so on. Okay. And so they behave like perfect players in an in-game instead of just one step ahead players. Okay, so instead of looking one step ahead and taking the best possible option they have right now, they wait and try to figure out what is the best possible option they will have a few steps later onwards.
Yeah, so this is more like saying, can they coordinate among themselves and get better partners, right?
Yes. So what if both sides do this? Then what will happen?
Yeah. So this is a.
So will the properties be the same, or will the properties be more average, or will the properties be even more like this? Because then maybe the men will figure out, because given they are thinking more than one step ahead, depends on will like get it better. So there are many. So from this it will go to a different range. But I want to know what is the range? Is it towards the men? Is it towards the women? Or is it in the middle?
Yeah, so this is not a question that I can immediately answer in one line. So we will keep this question and we will explore as and when, as we go on in the course. So there are several questions which I would like you to think about.
So, ma'am, regarding the 2 points that you've written on the screen, the 2 properties, we saw that men only get sadder and sadder and women tend to get better and better. So how does this men proposing algorithm give the worst possible stable partner to each woman?
Yes. So we will prove this. But then we don't have much time today to prove it. So we will do it tomorrow. Meanwhile, you can think about why this might be happening, or you might also come up with an example where this doesn't happen.
Okay, all right, ma'am. Thank you.
In the second example that we took, where M1 W1 M2 W2, in that case, there is, since it's only, it might be because there is only one pairing, there is no best or worse.
Yes.
Because there, so in any condition where there is only one, no, that is pretty trivial. Sorry, my bad.
Yeah, go ahead.
No, it's very trivial. If there is only one pairing, there is no better or worse.
Best and worst makes sense only when there are
Yeah,
multiple.
yeah.
So this is just something to think about. But a more concrete question is, can a man or a woman get a better partner by submitting false lists? So it is like, I am a participant. I don't reveal my true
Ma'am,
preference.
what do you mean by false list, ma'am?
Yes, I will tell you what it means. So for example, here, in this example, W3 gets the last partner M3, right? So W3 can ask herself, instead of giving my list as M1, M2, M3, if I give some other list, say M1, M3, M2 or something, if I change my list, am I going to get a better partner? Okay, or even W2 can think like that, that instead of getting the second choice, is it possible for me to change my list and get the first choice, the true first choice, of course. So,
Ma'am, can you scroll down to the questions for a second? Okay, thank you.
so these are, you can simply play with some examples. These are not the questions which you can possibly answer immediately, but just playing with some examples will give you an idea whether it is possible to kind of fool the system by submitting false list. It is like cheating. I don't reveal my true preferences, but I try to game the system by giving false ones. So we will also see more about this. Yeah. In the second question, do the women know the preferences of men? We assume that the preference lists are public, because there is really nothing to gain in the procedure by having the list secret. So yes, we can assume everybody knows everybody's list.
Ma'am, in the case of submitting false lists,
So these two properties I have not proved. I will prove them tomorrow, and we will also eventually look at whether it is possible to cheat the algorithm by submitting false lists. And there are, as I said, many more properties that stable matchings have, which we have not explored today. We will also explore them.
No, the fact that when proposing gives the best possible partner, although they're they're only getting worse in the algorithm. I mean, they start from a position which is most advantageous to them, as in they always start with their best choices. So, I mean, it would naturally give them the best possible partner, because if they got, if there was somehow a way for them to get a better partner, then that person will their partner will again get a better partner, and then that woman's partner will again get a better partner, and so on. But that will obviously lead to a contradiction somewhere, because this can go on forever since there are
No,
finite.
not necessarily. Maybe there are. Maybe it is more like in certain cases, then there exists this technique.
No,
Otherwise,
I mean, like, if you
so if in all cases, then that's actually possible. But otherwise, it is most probably not the case.
Ma'am, what exactly would be better or worse? Because in the first example, it was very clear cut that first preferences are, if everybody gets their first preference, it's always better than not getting. But in more complicated questions, how do we find out what is better for men or what is better for women? So it might be that in a
I will tell you what better and worse means. There is also one question which says which asks me to repeat what is false list. So false list is just submitting something else. So instead of saying M1, M2, M3, I might submit M1, M3, M2 if it is going to benefit me, or some other M2, M3, M1, any other permutation if it is going to give me actually better true partner. So I keep in mind that I like M1 the most and then M2 and then M3, but I don't write this list on paper. I write some other list so that I will get a better partner than what this algorithm will give me if I reveal my true list. So that is the false list. Anyway, we will explore the false list more and I will also explain more at that time. Here about the properties, what better or worse means. So we look at a man's list. Okay, I will come to the raised hand in a minute. So we'll take suppose M1. Let's say here. So take suppose M1. Look at what all possible partners M1 has in different stable matchings. Out of that, look at the best stable partner. Similarly, do this for M2 and do this for M3. It's like listing out all stable matchings, giving the best one to every man. That itself will be a stable matching, and that will be given by the algorithm that I have described today.
Ma'am, Omkar here. Just a reminder that we are running out of time.
Yes, I'm willing to stop. I just see your raised hands.
So, yes.
Mohammed.
Yes, my question is like this thing is that if this was a game among some like 4 or 5 people, then it's not a problem, but like what if it is something like college, or if it's something related to hospitals or something related to companies, wouldn't this be not legit? What this cheating list thing? Then how can we use this?
That's it. So we should in fact try to show that nobody can cheat here, but that is not quite possible. I mean, no system is foolproof.
Okay, then this is just general question.
Yeah. So
okay.
It is not possible to have always a truthful mechanism. I mean, it's a complicated thing to say at this point. I just asked you to try as a game, like take a few men and few women and try out whether they can get a better partner by cheating. So this is just for you to try out at home, that's all. But we will address this question later in more detail. So since we are now out of time, I think we should stop and continue tomorrow. Is that okay?
Okay, ma'am.
You can have your questions and ask me tomorrow, and you can also play with some examples like this and see what all can happen.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.